first talk of the afternoon, which will be Andrea Day from Harvard, who will tell us about string correlators on ADS3. Please.
So hello, everyone. I'm very happy to be here. I have the chance to talk with you and learn from you. And now I will report you, I will explain a series of work that I have been doing with Lorenz Eberhardt on string correlators on ADS3. So what is the motivation? Why do I care of strings and ADS? It's because I want to study holography, and I want to study holography beyond protected quantities. And then this is a hard task, so I want to find the easiest setup that is the easiest version I can have of the problem. And one of the easiest setups is ADS3 with pure and SNS flux. And this is because I know what is the worldsheet theory, so what is the 2D CFT on the worldsheet that realizes string theory. And this is the so-called SL2R Vezzomino-Witten model. So you might have heard of the SU2 Vezzomino-Witten model. This is the non-compact cousin of it. And this model is believed to be solvable. So we might get to a full control over string theory, but this doesn't mean that it has already been solved. So this is still a work in progress. And let me try to explain why this is still a work in progress and what are the difficulties. So the main novelty is the so-called spectral flow, which is a feature that is particular of ADS3 that you don't find in flat space or in ADS5. And now let me try to introduce this concept through a cartoon. So the cartoon might sound silly to experts, but I think it's good if you never heard these words before. So I will study correlators on Euclidean ADS3. So there is no problem if instead of thinking of ADS3 as a cylinder, I think instead as a sphere. And so this ball is ADS3, and the external surface is where the boundary CFT lives. The internal volume is my Euclidean ADS3. And this bluish surface is the worldsheet of the string. And you see that this surface is attached at 4 points to the boundary. So this is the pictorial description of 4 asymptotic states. So this is the cartoon of a 4-point function in ADS3. And so each of these is an insertion point, a vertex operator in string language. And if you zoom in close to the insertion point, you see that there are multiple sheets of this surface close to each insertion point. For example, in this one, I zoomed in, there are 2. But in general, you can have any integer, so you could have 3, 4, and different configurations can appear. And this is the pictorial explanation of the spectral flow. So spectral flow will be the integer that labels this winding close to the insertion point on the boundary. And yes.
From this, maybe it's trying from the pictorial, but is there an easy way to say why you wouldn't draw such a picture in ADS5?
No, I mean, the truth is that you study the representation theory in ADS3, and you see that you need this quantum number and to organize the spectrum in spectrally flowed representations. And then after you go through all the technicalities, you ask yourself, how can in one slide summarize all this? And is through this cartoon, but of course, I mean, it has the limitations of a cartoon.
ADS5, there won't be wound strings sort that extend all the way up.
Okay, you mean they will be localized to the center? I see. Okay, that's probably a better answer. Okay, so on the one hand, we see that we do have this winding and observables that carry the amount of spectral flow. On the other hand, there is an imbalance if you look in the literature, because so the spectrum is well understood since 20 years after the work of Maldacena and Oguri. But regarding correlators, much more is known on correlators that do not carry any winding with no spectral flow than with correlators with winding. So when we have no spectral flow at all, for example, we know a closed form formula for 3-point functions. So you can write in one line the formula for 3-point functions, and n-point functions can be related to Liouville correlators. And we understand how to compute the conformal block decomposition, and even crossing symmetry has been checked. But when we go to examples with winding, there are very few examples, and there are some special limits. But even the example with 1, 1, 1, so 3 units of spectral flow for the 3 vertex operators for a 3-point function is not known. And of course, we would like a general formula for all values of winding and understanding fusion roots, conformal blocks, and finally proving crossing symmetry. So during the talk, I won't be able to do all these points. This is the list of my dreams, but some of these you will see that we'll have an answer. And the general effort is going towards solving this 2D CFT. So let me start with some introduction. I want to introduce what are the protagonists of the game. So what are the vertex operators that capture these insertion to this boundary, these cartoon insertions. And then I need just a couple of slides of math, but I promise it will be quick and plenty of examples, so not be scared. So what is the setup? So I'm studying genus 0 bosonic string theory. And the strategy that I will follow is nothing deeply new or deeply original. It's just imposing all the symmetries that the model possesses and solving them simultaneously. And by symmetry, I especially have in mind the symmetry on the worldsheet, which is the so-called Kac-Moody SL2R algebra. So here you have the commutation relations, and I didn't put them here because you need to memorize them, but just because I want to underline that essentially everything I will say is a consequence just of these commutation relations. And remember, we have 3 currents. They are denoted by J, and I have a J plus, a J minus, and a J3. And they will enter this game because they capture the symmetries of the model. Okay, let me start from the vertex operators in the sector with no spectral flow. So the one where the literature is more rich and what they do look like. So I have a Z coordinate. This is the coordinate on the worldsheet. So it's the coordinate on this bluish surface in the cartoon. And then I also have a coordinate X, which is the point on the boundary of the sphere where my asymptotic state is attached. So if I go back to my picture, these 4 points would be X1, X2, X3, X4, okay? And then, okay, I have a spin, the SL2R spin. This labels the different representations that are contained in my spectrum. And most important, there is a big 0. So this big 0 reminds we have 0 spectral flow for these vertex operators. And you see that we know what are the OPEs of the currents with the vertex operator. So this is a synonym of representation of the symmetry algebra. So we know how the currents act on the vertex operator. And you see that it's relatively simple. I mean, we just have a simple form. But things become a bit more involved when you do have units of spectral flow. So the first sign, you see that the 0 is gone, and now we have a W integer that underlines that now we do have spectral flow. And if you think for a moment to the fact that we have 2 coordinates, one on the worldsheet and one in the boundary, and that we have a CFT on the worldsheet, but also a CFT on the boundary, it's natural that we need 2 parameters to capture the conformal weight for transformations on the worldsheet and transformations on the boundary. So it's natural that we have 2 quantum numbers that label these different conformal dimensions, and these are J and H. So H is what the dual spacetime CFT is the conformal dimension. J is again the spin, and in terms of these 2, I can label the 2 conformal dimensions on the worldsheet and on the boundary. It just happens that when the spectral flow is 0, they coincide. So the spectrally flowed case has one extra parameter. So this is the first difficulty that you see with spectral flow. And the other one is that the OPEs, so my representations, are no longer as easy as before, but they have higher ordered poles. And I didn't want to include here because they are ugly. You will see some slides later, but you have orders up to W. Okay, so now, yes. Yes, W is non-negative.
Yeah. Why the other way, or?
No, so in this picture where you have this X dependence, no, because essentially winding the other way would be, is like mapping essentially 0 to infinity, having in state versus out state. And you can have this map also doing global world identities on this X and Z. So they are already contained in this way of writing. But different conventions where you switch off this X, then you can have both positive and negative, and this is one of the technicalities. But in this setup, for me, it will only be positive, and this is enough. Okay, now comes the math, but it will be not so heavy. So we already heard various times in this conference the appearance of covering map. So let me give my working definition. So for me, it will be a map from the sphere to the sphere that is holomorphic and has finitely many ramification points. And the hands-on definition will be that it must admit a Taylor expansion around these ramification points Zi of this form. So what is this form? You see that the Zi are mapped to the Xi. And then in the Taylor expansion, you have many orders that are actually missing. And the first non-vanishing term in the Taylor expansion is the one with Wi power. Okay, so I missed the first Wi minus 1 terms, and the first non-missing is the Wi. Now, you see that this map depends on the choice of the Zi's, on the choice of the Xi's, and of the Wi's. So if I choose all these parameters at will, I do any favorite choice, in general, I do not find such a map. Okay, so the existence of this map requires some relations among these parameters that define the map. Okay, and another information I need is how you compute the degree of the covering map. So this is a covering map. So if I ask you how many times am I covering the sphere, 2 times or 3 times, how compute this? So this is just a linear combination of these Wi's. So you have to sum them with some shift, and this is the answer. Okay, so in order not to be scared by these covering maps, let's find what is the covering map in an example, and we consider 4 ramification points that have ramification indices 2, 2, 1, and 1. So the first thing I do to simplify my life is to fix 3 points, 3 of the Xi's and 3 of the Zi's to sit at 0, 1, and infinity. And then I will have a residual dependence on the 4th coordinate that I call X and Z. Now, I can compute what is the degree of the cover. I just have to sum these W's with some shift. So if you insert these in the formula of the previous slide, you find that this choice of ramification indices has degree 2. So the map I'm looking for is holomorphic. So it's the ratio of 2 polynomials. And the fact that it's degree 2, it means the polynomial in the numerator should be of order 2. And then I know that at infinity, which is the point, is the 3rd insertion here, it should go linearly. That's the meaning of that 1 there. So going linearly, it means that the denominator should be degree 1, so that the whole ratio is going linearly at infinity. And this is my answer. So A, B, C, D, E are free parameters. So I have 4 free parameters. And then I'm very naive at this, and I just impose the Taylor expansion that I presented before. So first I should impose that 0 is mapped to 0. You remember Xi is mapped to Zi, and 1 is mapped to 1. But then having spectral flow 2, the Taylor coefficients up to the first should vanish. So this means that gamma prime of 0 should be 0, and gamma prime of 1 should be 0. And you see I have 4 conditions, 4 free parameters, and this fixes the map uniquely. If you do this exercise, this is the solution you found. Good, we have found the map, but if you pause for a moment, you realize that, okay, I have imposed the behavior at infinity, at 0, at 1, but not the behavior at x. So I should still impose that z is mapped to x. But on the other hand, I don't have any free parameter. So the only hope is that x and z are themselves already related in such a way that gamma of z is x. So a covering map does exist only if gamma of z is x, or if you raise the denominator in this equation, if this polynomial here has a 0. And so you can repackage the requirement for existence of a covering map into zeros of a polynomial. So for every choice of ramification indices, you can assign a polynomial that when this polynomial has a 0, a covering map does exist. Otherwise, there is no covering map. And of course, you can repeat this game with many different ramification indices. And the higher the W's, the more complicated these polynomials. But there are algorithms to implement this in Mathematica that are more intelligent than what I was presenting, but that have the same spirit. Okay, now we are done with the math, and we can come to the meat of the talk, which is providing a closed form formula for correlators that do carry spectral flow with all parameters generic. So we don't want special limits. There are plenty of results on special limits, but we want the most generic one. And again, the strategy is just listing all the symmetries that we know these correlators should obey and solving them simultaneously. So let me try to go through these various symmetries. So we have global symmetries. By this, I mean global word identities. Our correlator should be translation invariants, and then I should be able to do rotation, special conformal transformations, and so on. But conformal symmetry is much more than global transformations. I have the whole power of Kac-Moody currents. So I can also impose the constraints that affine symmetry requires correlators to obey. And then I will impose the Knizhnik-Zamolodchikov equation. I will explain in a few slides where this comes from, but it's an additional requirement that my correlators should satisfy. And then in the spectrum, for some special values of the quantum numbers of the spins, the spectrum contains some states that are actually the 0 vector. So if I insert the 0 vector in a correlation function, that correlation function should vanish. So this means that the generic correlation function should vanish when I specialize the quantum numbers to these special values. So what we do, so the limitation of our technology is that we are not able to write these all these constraints in closed form as a function of W. But we can write them explicitly as soon as you give me an assignment of W's that are not too large and exhaust my computational power. But for many examples, we can compute this. And if you keep doing this exercise and again, you start learning that as you change W, the general structure doesn't change so much. And you start saying, okay, maybe I have an idea of what is the general formula for whatever W we fix. And then you can probe for more and more cases that this is indeed the right guess. And we check this in more than 1,000 examples. So that's why we believe this formula is true, but on the other hand, it's a very hands-on approach, and it doesn't constitute a proof. But the take-home message is that through the formula I will present, one is able to translate all the knowledge about the correlator with no spectral flow to the correlators that do carry spectral flow. And so through this map, we should be able to transfer all the knowledge about conformal blocks, crossing symmetry, OPs, a general formula to the correlator with spectral flow. So we haven't achieved all this, but that's the mantra of the talk, essentially. Okay, and now I want to go through these various symmetries a bit more in detail so that you appreciate what are the technicalities and what are the new ingredients that we have. So global word identities are the easy part. So they just allow me to fix 3 insertion points and get rid of these xi's and i's. So I just fix them to be 0, 1, and infinity. Remember that I have them on the worldsheet, but also in the space-time. So both the xi's and the zi's I can fix. And then I have 2 cross ratios in the boundary and on the worldsheet. What is more difficult is affine symmetry, but also very more powerful. So I have the whole tower of J currents, and I have to understand how to translate this symmetry at the level of correlators. And this was understood around 3 years ago. And so you see, if you stare at the first line, this is the OPE that I didn't want to include before. And you see that I have pose up to order W+1. So this is ugly. But on the other hand, there is a special combination of currents, the J+, J3, and J- that I was mentioning before. There is a special combination that not only has no pole, but is very, very regular. So up to order W-1 is 0. So I can then compute a correlation function with insertion of this thing, and whatever crap I obtain, I Taylor expansion up to order W-2, and I impose that each order in the Taylor expansion is 0. So I get a system, and solving this system, I'm constraining correlators. Now, the good news is that we do have control on the constraints that follow from affine symmetry. The bad news is that they are ugly, even if the spectral flow is quite low. So this is an endpoint functions where I have all values of spectral flow to be 1. And you see that it is, on the one hand, it's a differential equation because I have derivatives in the xi's which have not been fixed. And at the same time, it's a recursion relation because the values of the hi's here is shifted down, here nothing is shifted, and here a different hi is shifted up. So I don't know how you want to call there, something like differential recursion relations, something of this sort. So that was the main technicality we had to face. And the way we approach this is to adopt a Fourier-like transform, so an integral transform that turns the recursion relations that we are not good at solving in partial differential equations. So it's true that it's partial differential equation, it's not an ordinary differential equation, but it's linear. So it's still, you can still play with it. And you have one of these equations. So here at the end of the slide is what the equation of the previous slide becomes in this Y language. So you see in this transform, I have traded the variable that was shifted, this H, I have traded for a continuous variable, auxiliary variable, that is this Y. So in the next few slides, you will no longer see the H's, but you will see correlators that have between the X and the Z, you'll see a Y, okay? Just think of this as a Fourier transform. We don't have position, we have momentum, and here the analogies, we don't have H, we have Y. Now, we have 4 of these differential equations. Yes, now I'll come. We have a system with 4 of these differential equations. We have to solve them simultaneously, but you can do in mathematics. I mean, if you are patient and you convince Mathematica, you can solve this. And once you have solved this, you say, okay, I succeeded with 1, 1, 1, 1 as choices of spectral flow. Let me try 1, 1, 2, 2. And you go up. Yes, there is a question.
Yeah, how should I think of this Y variable? Like, I know that there's a mathematical Fourier-like transform, but how should I physically think of it?
I wish I knew. And that's essentially what our work doesn't touch. So there should be a geometric interpretation of our algebraic story, but we have a very poor understanding of this. So at this level, it's just a math trick that simplifies the equations. But I agree that there should be a physical or geometrical explanation of why the problem is simpler in these variables.
So
did the worldsheet shift with Knizhnik model, but what about the space-time shift?
Yes, I will come to this. So I agree. So my motivation was holography, and it's right that you should complain that I'm talking only about strings in the bulk at the moment. But this is because it's much, I mean, if I want a duality which is exact, so that also captures protected observables, much more is known about the string theory than the dual CFT. So I have to study string theory in order to formulate a good guess for the boundary CFT. Okay, I will come to some proposals that have been formulated, but they have been formulated by studying string theory essentially. So the situation is not even. Much more is known about string theory, despite it's more complicated than about the dual. Okay, so what is the solution I find when I solve all these all of these partial differential equations, and I keep doing this game with different values of W? What do I find? I find a structure that is neat given the complication of the differential equations I was solving. And let me try to introduce the structure I find with an analogy. So if I was solving not affine symmetry constraints, but global symmetries constraints, and I was not in the flowed sector, but in the sector with no spectral flow, then what I would have to do to constrain the xi dependence is just opening my favorite CFT book, and one of the first chapters tells you that you can fix the xi dependence up to an unknown function of the cross ratio. And you have in front of this unknown function a dependence on some difference of the insertion points, so something like x1 minus x2, x2 minus x3, and so on. And the coefficients are a linear combination of the conformal weights. And remember that in CFT, in this CFT, the conformal weight H in the unflowed sector is J. Okay, so this is nothing really deep. It's just different chapter 4 or 5, something like this. But now the problem that we actually wanted to solve was solving the constraint from affine symmetries, not global, and in the flowed sector, not in the unflowed. But I wish I knew why, but I don't. But the answer we find is very similar in structure. And you see that here, what was the difference, x1 minus x2, now is replaced from what we like to call generalized difference, is this capital xy2, that is no longer the difference of something with label 1 and something with label 2, but is a function of the auxiliary variables y1, y2, and of the cross ratios x and z. But beyond this is the same expression, because I have the same exponents, the same couples of 1, 2, 1, 3, etc. And again, I have an unknown function of what I would like to call generalized cross ratio, because it is a combination of these capital X's in the same shape that the true differences xi minus xj, they were combined. Now, you should complain that I'm not giving you the definition of this x, so here it is. So I can give you the closed form of the definition of these xi's, but then we spend 15 minutes decoding it, so I prefer to give examples. So I can define for x empty set, and this is just the polynomial that encodes the existence of a covering map with ramification indices y1, y2, y3, y4, the one I presented before. And if instead I look at x1, 2, this will be a linear combinations in the auxiliary variables that I introduced, the y1 and y2, and the coefficients are again these polynomials that encode the existence of a covering map. But now I start playing with the levels, and you see that when I have a W1, I shift down the associated W, and when I don't have it, I shift the W up. And in this way, I write all the terms that I can, so both W1 and W2, sorry, both Y1 and Y2, just one of these, or none, and I shift up when there is not the Y, and down when there is. Okay, so I think you can now deduce or guess what is the x23 or x34. Now, I promised you a closed form formula. This is not yet so, right? Because this function f, it's any function. It's an unknown function that is not constrained, but is affine symmetries. So if I want a closed formula, I should understand what is this unknown function f. And in my list of symmetries, I had another one, which is this Knizhnik-Zamolodchikov equation. So now I can impose this on the solution I find and see whether this constrains further the dependence of this f unknown function. Okay, let me quickly review where this Knizhnik-Zamolodchikov equation comes from. So it's just the observation that the translation operator on the worldsheet, so what you would call d by dz, the derivative with respect to z, is the Virasoro minus 1 mode, so L minus 1. But the Virasoro mode is a bilinear in the currents. And we know the action of the currents on the V's. So in this equation, we know the left-hand side, because of course we know how to take derivatives. But we also know the right-hand side, because we know how currents act on vertex operators. So we know the left-hand side, we know the right-hand side. Let's insert this equation inside the correlator. So this will give rise to a differential equation for the correlator that is first order in Z, this you see, and second order in the axis, because it's you have two J's. Okay, so when I do this, the first surprise is that the differential equation that I impose on my answers reduces to the unknown function f. So this shows that this differential equation is consistent with the affine symmetry constraints. But the first surprise is that the differential equation that the function f should obey does not depend on the wi's. So in principle, since I'm solving this problem every time with different w of the spectral flow parameters, in principle, I should have written f that depends on w1, w2, w3, w4. But I always find the same differential equation, independent of the w's. So the dependence of the w's has been washed away. And then I try to solve this differential equation, but it's coupled, second order, and we are not able to solve it. On the other hand, if you search in the literature, you see that we were not the first to study this differential equation. And the differential equation that f should obey is the Knizhnik-Zamolodchikov equation that the correlator with no spectral flow would obey. And if you repeat this game for null vectors, the same story comes out. So the differential equation for the null vector in the flowed sector imposes a differential equation on the unknown function f that does not depend on spectral flow, and that coincides with the null vector equation that the correlator with no spectral flow would obey. So we believe that this is not a proof, but it's enough of a motivation to say that, okay, the unknown function f is the unflowed correlator. After all, it solves the same differential equation. So at this stage, we have a complete formula for our 4-point function. And it's a 3-line formula. It might seem ugly, but by now you know all the ingredients. So let me review this. So the left-hand side is the goal of the talk, a 4-point functions of vertex operators in SL2R Vezumino-Witten mode. And the right-hand side is the solution of the problem. So let me start from the second line. So we have introduced these generalized differences that are functions of the auxiliary variables yi's. There are linear combination of these yi's, and the coefficients in these linear combinations are the polynomials that encode the existence of a covering map with some shifts of the wi's up or down. And then we said that there is an unknown dependence, but actually this unknown dependence is known, is the unflowed correlator. So the correlator has been studied much more deeply in the literature than this one. And then this solution we obtained by the trick of going to these y auxiliary variables, but we preferred, after all, the original variables where we feel more comfortable. So what we have to do to translate is just to Fourier transform back. And this is what this integral achieves. So it translates the answer back to the old h variables. So the take-home message is that correlators that have spectral flow inherit properties from correlators that carry no spectral flow through this formula. And that is the roadmap to deduce all the nice properties we know for the unflowed correlator, also translate them to the flowed sector. Okay, so now someone should raise the hand and complain, because if you really stare at the answer I gave, there are various properties that are really basic and you cannot renounce that are far from manifest. So for example, you could start saying, okay, you have a bosonic theory. So if you exchange two of your V's, nothing should happen. So you can achieve this by swapping the label 1 and the label 2 for vertex operator at x1, z1 and x2, z2. And your formula should be invariant under this change. And if you stare at the formula I gave before, it's far from evident that this happens. And then someone else that is more familiar with this model might say, okay, but you also have continuous representations in the model, and similarly to Liouville theory, the spin j and the spin 1 minus j representation are actually the same. Is it manifest that your formula doesn't change if I swap j for 1 minus j? It's not manifest. And then a few special results were computed in the literature by other techniques. Does our formula reduce and reproduce those cases? So the formula passes all these checks, but in order to prove that indeed we have all these properties, we have to rely on a set of mathematical identities that again we can check in Mathematica, but we don't find references in the math literature. So we are sure they are correct because we have tested deeply, so they satisfy a physicist taste, but they wouldn't satisfy a mathematics taste, a mathematician taste, because we have no proof for them. So, but we are essentially predicting some new identities among these polynomials that encode the existence of a covering. And in one case, this is very nice because when I inserted this unknown function of a cross ratio, you might say, but why that cross ratio? You could find a different cross ratio, right? And this wouldn't change the answer, or it would change the answer in a well-known case at the level of the di Francesco for chapter. Does it happen the same way here? And it does. So you see that for the special properties of these polynomials, you see that 1 minus a certain generalized cross ratio is still another generalized cross ratio, as it would happen with the ordinary cross ratio that is in terms of xi minus xj. So yeah, the summary is that we don't know where these identities come from, but they are essential to check the consistency of the proposal. Okay, now we have a good toy. We have spent a lot of effort to find this formula. Let's use it for something. And the something is trying to study it to understand features of the string theory that also the boundary CFT should capture. And so features that can decide among different proposals for the boundary theory and can guide us to understand what is the correct boundary theory. And here now I present a research proposal for what the boundary theory could be. And at the level of this talk, you don't have to trust this proposal, but the approach is to test this proposal. So the proposal is the following, that the two-dimensional CFT that is dual to bosonic strings on ADS3 cross X, where X is the internal CFT, and they just require that it has the correct central charge for the string theory to be critical. It's compact and unitary. The dual is proposed to be the symmetric orbifold of a linear dilaton with a specific background charge across the internal CFT X. And this is not enough. You also have to deform it by a twist 2 operator. So the symmetric orbifold is an orbifold. So you have twisted sectors. Twisted sectors have a ground state, and in particular, one of the sectors is the twist 2 sector, and the sigma 2 is the ground state in that sector. So the proposal is that observables that can be computed by conformal perturbation theory in this approach from the dual should match the predictions from the bulk. And the map between the momentum of the linear dilaton and the spin in the bulk is this that you see on the screen. And this formulation is enough to predict that the boundary CFT, at least this proposal, this candidate for the boundary CFT, has a lattice, a two-dimensional lattice of poles. And we can compute the precise location of these poles for correlators in this proposed boundary CFT. Now, let's come back to the bulk and to our formula and see whether, to which level we can capture these features and whether this proposal that is just a candidate matches what we do know that string theory predicts. So then I want to ask, what are the singularities of my string correlators? So this comes from a 2D CFT. So usually in ordinary 2D CFT, you expect that your correlators are singular whenever two vertex operators come very close. And this you can rephrase in saying when the cross ratio becomes close to 0, 1, or infinity. But in this case, we also find many other singularities that are just in the middle of the moduli space, and they are not close to 0, 1, or infinity. But you have branch cuts that pop out when there is a special relation between the two cross ratios, x and z. And the special relation that gives rise to the location of the singularity is again captured by these polynomials. So every time that x and z are related as a zero of this polynomial, the one that encapsulates the existence of a covering map, up to some shifts of the ramification points, in all these cases, we find a branch cut in the worldsheet correlator that signals a divergence in the correlator. So this phenomenon and the physics behind it is not something that we understood. It's something that was understood long time ago by Maldacino and Noburi. And essentially, so at least in some easy examples, we can just recap what the Maldacino-Noburi explanation was. So for example, if you look when PW and XZ is 0, so this is when a covering map exists that can map the worldsheet to the boundary. So this means that the worldsheet is allowed to cover the boundary. So the worldsheet is allowed to travel all the way and just leave on the boundary. And this, of course, this means that a non-compact direction opens in the path integral that in particular integrates over the radial direction. And this gives rise to a volume divergence in the path integral. So our path integral description of correlation function is exploding, and this signals the divergence in the correlator. So we believe that what we find is just the generalization to different values of spectral flow of the phenomenon that was studied by Maldacino and Noburi. Yes?
Do you understand why this shifts up and down in the W's up here?
Qualitatively. So qualitatively, so there is an identification of representations. So in the spectrum, you have some continuous representations and some discrete. For the discrete representations, you have the highest weight and lowest weight, which are called plus and minus. And there is an identification. So it's something like D minus W spin J is D plus W minus 1, K halves minus J, or something like this. Don't mind me, it could be swapped plus and minus. But this means that if something diverges with a certain, if you have a divergence for a choice of spectral flow W, you should also have an associated divergence for W minus 1 if you just use this identification. So whatever location of the singularities you find has to respect this symmetry. So probably these plus minus shift, plus minus 1 shifts come from there, but I cannot honestly derive that the full set of, I mean, I cannot derive the location of the singularities just from this symmetry. At least I'm not able. I cannot exclude it can be done.
And this without changing x, without having, because the plus and the minus usually extract with 1 and 0, 1 and infinity. No?
Without changing x. I mean, of course, you have to be careful. So what I wrote is an identification of representations, yeah, not of states. So there is just one state that is primary in both of these representations. So generically, this means that a V plus, okay, a highest weight of plus is not equal to a V minus, but a V minus with insertions of J currents.
Right.
So to really exploit this, you should, I mean, you can only exploit when you don't have J insertions. In the generic case, you have to wrap all these J's and this generates a mess and it doesn't seem to be doable. Okay, but we can go on and say, okay, let's pick a particular example. Let's take PW equals 0, and there the correlator has a singularity. Let's zoom in close to this singularity and see what it looks like. And we can make our formula that I presented before much more explicit close to here. Essentially, what we are doing is Taylor expanding close to the location of the singularity. So think of x being fixed, some fixed number. Then there is a value of z that is a 0 of this polynomial, that is the location on the worldsheet where you find this, the origin of this branch cut. So we go close to there and we Taylor expand close to this location. And this is what we find. And not be scared by the long formula. It has a nice structure. So let me start from here. So of course, we are expanding around the location of the singularity, which is Z gamma. So it will be some Taylor term in as a power of Z minus Z gamma. Okay, so this is the obvious part. And then it will be a function of Z. And the function of Z is relatively simple, is Z times 1 minus Z to some powers. And then I have some gamma functions, okay? And the third line is some covering map information. So this is the residual of my PW covering map polynomials. They leave an imprint at this level of in this Taylor expansion. This is covering map data. So to be more precise, this capital pi is the product of the residues of the covering map. And these AIs are the coefficients of the first non-vanishing Taylor coefficient in the expansion. You remember I have this covering map, many Taylor coefficients were 0, and then the first non-zero was raised to the power WI, but it came with a coefficient in front, and this is the value of AI. So we can summarize this third line as covering map data. And then we have a Liouville correlator, so correlator in Liouville theory, because in these limits, we can exploit the fact that there is a relation between correlators of SL2R and correlators of Liouville. Okay, so we can now continue to play with this formula and say, okay, but I started saying that I'm interested in string theory, but it is not yet string theory. This is still 2D-CFT. So to turn this 4-point 2D-CFT correlator into a string theory correlator, I have to integrate over Z, right? And what happens if I integrate over Z? So my Z dependence is here. Now, if I tune this exponent to be in -1, so this is a special choice of parameters, but it's an allowed choice. So I tune this to be -1. I'm integrating, I'm doing the integral of 1 over Z. But the integral of 1 over Z diverges, right? So this means that when this exponent is equal to -1, or actually to any negative integer, this correlator develops a pole. Okay, and this is how the worldsheet sees the poles that the boundary theory predicts. And actually, in this case, we can also compute the residue of this pole. But in general, so this was just a specific example, but if you are a bit more patient and you look when this happens in the generic form, you can catalog the location of all these poles. Okay, now I went through the story for one of those, but you can do for the whole lattice of poles. And the lattice of poles that you find in the bulk is exactly the lattice of poles that this candidate CFT was hoping string theory would possess. So the pole structure, the pole lattice, and the location of these poles in the spins agrees with the location of poles that the boundary CFT would have desired. And we can actually do more. So in the special example that I told you, we can also compute the residue at the pole. We cannot do this always. It's kind of hard computation, but there is some special case where this computation is easier, and is the case I presented, and we can compute the residue. So you see that now I have double brackets. So by this I mean string theory correlator, meaning I have already performed the integration over Z. This is singular, meaning that I'm sitting on a pole, so the correct thing is computing the residue. So I'm computing the residue for a special choices of JIs. It was the special choice tuning my exponent to be -1. And this is the answer that I find. And each of these lines has a nice explanation. So the second line is, again, the same expression we had before, is covering map data. So it's still the signature that there are some covering maps involved in the game. And then if you stare at what is in the first line, you see that we have Z at some power and 1 minus Z at some power. And if you stare at the exponent of this Z and 1 minus Z, it factors in something that has label 1 times something that has label 4, something that has label 2 times label 4. And if you go back to the proposal for the momentum of the boundary CFT modes, this is exactly the combination of is what the boundary CFT observer would call P1 and P4. So you have Z to some P1, P4 times 1 minus Z to the P2, P4, but this is the correlator of the free boson, or if you prefer, since the momenta don't sum to 0, of a linear dilaton with background charge. And then you have, okay, still some gamma functions in front that are still important to see if we really get this correspondence up to every factor of gamma, k, and pi. And indeed, this is what we get. And these covering map data are actually not just random covering map data, but are exactly the signature of the presence of the symmetric orbifold. So I say this because when you compute correlation functions in a symmetric orbifold, if you start the final answer of the correlator in a symmetric orbifold looks like correlator of the seed theory, the theory I'm taking the symmetric orbifold of, times covering map data that take this form. Okay, so that have this product of the residues and these AI coefficients. So this second line is the signature of the presence of a symmetric orbifold. And you can check all the factors of K, of W, and all the normalization. It really turns out as it should. So I told you that the boundary theory was proposed to be not just the symmetric orbifold, but wasn't there also deformation? It doesn't seem to appear from the answer I get from string theory. And this is because the location of the pole that we looked at was particularly easy because we are looking at 0th order in conformal perturbation theory. So we are not detecting this deformation at the level of 4-point functions. So that's why the answer was easy and why we see a symmetric orbifold, but not yet a deformation of it. And so this is the final answer, and it exactly reproduces the CFT expectation, including factors of 2 and factors of pi. So let me try to summarize what I have tried to explain and what is the list of many things we don't yet understand. So we are proposing a full solution for the SL2 Zumino-Richter model, meaning that we are proposing a full set of 3 and 4-point functions, still on the sphere. And we are proposing a map to extract knowledge from the unflowed correlator and map all this knowledge to the flowed correlator, so that we have a control over correlators in general in the theory and observables in the SL2 Zumino-Richter model. We also decoded an intriguing pole structure and showed that the pole lattice that populates the string theory correlators exactly agrees with the pole structure that one of the recent proposals for the boundary CFT had predicted. And in one special case, when the computation is more doable, we can also check the residue. And this means that we are checking an example of ADS CFT. We are matching a 4-point function, which is non-protected, exactly in alpha prime. So this is what we can do, but there are many things that we are much weaker and we are not able to do, at least for now, or maybe never. So we still don't understand, for example, how the conformal blocks expansion works directly in the flowed sector. Of course, we can use this map and try to extract this information from this map, but from first principle, how it works in the flowed sector, we don't understand. And we also don't understand what is the OPE of 2 of these vertex operator V's. So you could have said, why are you suffering so much? So usually in easy examples of 2D CFTs, what you do is not inserting J currents and doing all this pain of word identities. You just take the OPE of 2 V's and they become another V. And this, until you get to 2-point functions, is much easier. True, but we have no idea what is the OPE of 2 of these V's. So it's not, we don't have a full control on this. And then everything I said is essentially algebraic, but there should be a geometric interpretation that explains why covering maps are around, what is the meaning of this Y variable, why there is kind of a global word identity that carry out to keep these exponents. All this we don't understand, but there should be a physical explanation making everyone happy. And then we checked only one residue, which is 0th order conformal perturbation theory. Would be nice to check this a bit more extensively. It has been done by the paper in the Lawrence paper for 3-point functions, but in principle, you can also do for 4-point functions. Of course, it's more of a pain. We pick the easiest one. And then all this is a bosonic story. String theory is only consistent as a superstring theory. So the final duality wants to be supersymmetric. So in principle, the technology is there. If the RNS formalist, one has to learn it and apply. We should be able to compute supersymmetric correlators. And then computing correlators in other backgrounds. This is actually, apparently, since having seen the talks this week, not a future direction, but a present directions that people here are pursuing. So knowing ADS3 is an important data for other backgrounds. So microstate backgrounds, as we heard from Nicholas, but also Euclidean BTZ or anything that you can deduce from the behavior of ADS3. And finally, the approach we took is not the one that was presented by Knizhnik-Zamolodchikov or Maldacino-Guri, so it was not the approach that was usually in the literature. We can recover the results, but we can just see that the final answer is the same. We honestly don't understand by first principle why their approach should be equivalent to ours. It just is in all known examples, but it would be nice to understand better that we are doing by first principle the same thing. So these are essentially my questions, But at this stage, I think you have right to ask your questions. So thank you very much for your attention. Thank you.
So let me put it this way. So in your paper, I think you guys say that this proposal is strictly for n goes to infinity, the fundamental string charge to infinity. Else, this identification of the symmetry product was because long strings are strongly coupled for k greater than 1. This story comes in. Exactly where in your calculation you are using that you are working at strictly n equals infinity?
Okay, so first of all, this proposal is just by Lawrence. It's a single author paper. And the proposal, only, you're right, only captures the large n behavior. So it's has the ambition to be true only at strictly n equal infinity. So there is no prediction that this has a hope to work at finite n. And where, so what does it mean? Now you should ask, what does n equal infinity means in my computation? I'm essentially just doing string theory and comparing with the formula from this proposal. And in string theory, it means G string should be close to 0. So it means that I'm taking the 3-level computation. That is actually the only one I'm able to do.
Right.
So what this means is that I only had to care about the sphere correlator and not the torus correlator or double donut correlator and higher G's. Luckily, otherwise I wouldn't be able to compute anything in string theory. So that's where it
enters. On the field theory side, it's coming in through.
So on the field theory side, the proposal itself is only formulated for large n. So it comes in at every page from page 1 to the last page, essentially. I mean, this n, if it's not clear to everyone, is the number of copies I have in my symmetric order.
On the supersymmetric case, because the mantra of this talk, as you said, is basically shifting the properties of the unflowed correlator to the flowed one up to this factor of 1. Have you tried to see whether this happens also with an insertion of the current? Have you already did some computation to check that actually this again happens modulo the change in the shift of j, because the weight in that case is just a shifted version depending on whether you're an s or a 1 you have a shift.
No. So, okay, let me try to elaborate the question. So maybe also the others can appreciate. So he's asking, when you go computing supersymmetric correlators, the challenge is that we have to consider picture changing. So it means that I'm not really allowed to compute vertex operators of vertex operators dressed with fermions, but for some of them, I also have to act with the G minus a half, so the current dual to the stress tensor. And the effect inside correlators is that these I have to compute not the correlators I have, but correlators with an insertion of a J current. So I don't need, for example, for supersymmetric 3-point functions, I don't need the VVV correlator I computed, but I actually need a J VVV 4-point function. So we haven't started to do this, but certainly the approach could be the same. I mean, it certainly works to, again, hit this stuff with another J, but it's a bit of a pain that we are a bit lazy to repeat because this was a pain. So another way could be try to deduce from the 4-point function with 4 V's, try to inspect whether this is related to a 4-point function where one is a J and the other 3 are V's.
There's already for 3-point function, right? So instead of doing it for 4, 1.
Yes, but computing a 3-point function where you have 1 J and 2 V's would have no motivation.
No, 3 V's and 1 J.
Yes. Already for that, you have to do it.
Okay, let's have one last question.
Just curious about the generalized cross-raters. And you were talking about the geometric interpretation. Are there just like covering space cross-raters in some sense? Or?
Yeah, this we don't know. I mean, we know that the right variables are these PWs and these capital X. But why they are the right variables, we don't understand. I mean, there should be an explanation, a formulation of this problem that starts already in terms of these capital Xi variables that must have some geometric interpretation, and that directly gets to our formula as a product of Xi's and makes manifest this symmetry that looks like as it was a global symmetry. But that's just what we hope, but we are far from understanding this.
Okay, I propose we postpone further questions for coffee. So let's thank Andrea again.
Thank you very much.